So some basic announcements here. So chapter 8 will be due a week from today, next Thursday. So go ahead and start reading that and all of the associated perusal, reading exercising, reading assessment. You've had an assignment E2, that's been out for a while, that gives you practice on using sliders, delays, units, those sorts of things. There's basically two major questions, and then a third question, the bonus question. The first one is on everything but delays. The second one's on delays, and the third one's kind of also about delays. And that is due this upcoming Sunday. Then there is an assignment that we formally will release today. I mean, it's been available, but we're going to basically talk about it all day today. And then on Tuesday, instead of having another lecture, we will meet at the lecture period, but it'll be a time for you to work on this assignment. And then in, say, breakout rooms, and then I can go around and provide any additional assistance, because this assignment E5, which we're talking about today, is your last homework assignment. It's meant to be kind of a mini project where I basically do most of the work for you, but to build a kind of, so I give you a recipe that has a few kind of fill in the blank spots that you have to do for a stock and flow diagram that's on the order of what you would expect for your final project. And then after that, the only other big deliverable you have is the stuff in your final project. So then a little bit later, so this is a week from Tuesday, we will have another one of these things where instead of a lecture, we'll have an open period where we all come to class, but then Eric and I will move around the class, and you'll have to demonstrate to us by the end of the class that you have implemented a basic version of your model, not necessarily your full model, but a version that shows that you feel comfortable getting things up and running in Vensim or Insight Maker, and you can start getting results that at least move in the right directions. You might need to add a lot more before you're done with your final project, but it at least shows us that you've got momentum moving forward. And if you can't manage to do that at the end, by the end of the class, then you'll end up making a video demo that you'll upload to Canvas instead, and then I'll take a look at those offline. So that's kind of our timeline for going forward, the nearest things here. So just start reading the chapter, finish this assignment. If you'd like, start this assignment, but it'll be due in a week from Sunday. And then with your groups, you can start thinking about what is this kind of basic stock and flow model going to look like. And I guess I could add in here this, since I extended it a little bit, your final project proposal, if you want to submit revisions, those are due Sunday. And so I already graded all the final project proposals for all the groups. I provided a lot of comments. Everybody's got a score. If you're happy with that score and those comments, then that's fine. You can leave it alone. If you'd like to get some of those points back, you can feel free to resubmit, taking care of the comments that I made for you, and then I can then regrade your resubmission and give you a totally new grade. And so that's a way you could potentially get all the points back if you'd like them. Or again, if you're happy with your score, you can just leave it alone, and we'll just leave it at the old assignment. So that is an option that I've made available to you, so that you have that. All right, so any questions about the timeline moving forward before we jump into this assignment E5 overview? Okay. All right, in that case, let's flip to the PowerPoint here. All right, so like I said, today it's mainly about explaining this assignment E5, which will be due a week from Sunday. And this assignment was kind of motivated by this EasyJet example that was at the end of the chapter that we talked about on Tuesday, chapter 6. And so if you remember with that EasyJet example, they basically talked about how you can take a sector of EasyJet here, which is kind of just how you would like if you're EasyJet, you would like to model how your company is going to grow over time, and you'd like to maximize that growth. And so you end up building a sector that has to do with the growth of your company. And then you start thinking about what are the potential challenges that could get in the way of your growth, and having to model them in there so that you can kind of think strategically about that moving forward. So you have another sector of your rivals. And so these rivals are going to interact with you through their fare and your fare. And so as you set a fare lower than them, then they're going to restructure their business operations so that they can over time lower their fare to be more competitive with you. And that's going to take away from your growth. And so we can model the growth in EasyJet, and then we can also model the restructuring process in the rivals. Those can be modeled sort of separately as two separate sectors. And then those two can be connected together through the relative fare, which is just a comparison of the startup fare from EasyJet and the rivals fare from the existing competitors that are in the market. And that kind of is a plug that allows these two Lego bricks to come in together and start interacting with each other. And then there are additional complicating factors that can be added on top of that. So and along with the competition you get from the rivals that you're trying to kind of get an edge on, you have to deal with other processes that limit your growth. And for example, route saturation. So there's a general fundamental limit in how far the new arrival can possibly grow, and the rivals are going to further reduce that. So we need to model both the kind of fundamental limits as well as the limits from the competitors. So those are three sectors that were bolted on together in building this model. Now I'm showing you the causal loop diagrams, but in chapter 6, they did go into the stock and flow diagrams for at least most of the components of these sectors. And so what I'm not showing you here is that when you build a sector like this, once you kind of identify the important variables, the next step is to then, just for that sector, develop a stock and flow diagram, which adds the dynamics into it, which really says, as when we have this many passengers, we're expecting a growth rate of this. But as the passengers increase, then the growth rate is going to slow. And so how is that going to change things over time? Those are the dynamics that we put into the stock and flow. So you can imagine building stock and flow models for this sector, stock and flow models for this sector, and then plugging them in together inside Vensim. So motivated by that, then what I've given you in assignment E5 is a similar sort of operation here, where you're going to be modeling sectors independently and then connecting them together and then studying the interconnection. And so I just want to say ahead of time that this particular model, which is supposed to be a model of coupled population dynamics and municipal water dynamics, is not really a good model. So it was not, I didn't want to put together a really good model of something that some of you might decide that you wanted to model anyway in your final projects. And so I didn't want to compete with you on your final projects to sort of say, oh shoot, we ended up choosing the exact same models in assignment E5, we need to choose something else. So assignment E5 kind of has all the right components to what you need in a final project, but it's not really a really good model of population and water dynamics. So it's meant to sort of be an exercise in the process, although the model itself has a lot to be improved upon. And that hopefully then allows it to not compete with the models that some of you were going to build. Because I think at least two groups have thought about the idea of population growth and urban dynamics and mixing together. And so that's kind of what this is getting at. But this one is, I didn't quite spend a lot of time coming up with a good model for this. So that's just a caveat looking forward here. All right, so the idea in this assignment is that the first thing you worry about is the population, let's say, of a city. And so there's going to be a sector for population, which is going to keep track of how many people live in the city, the births going into that, how the population grows, the deaths. And you are in the assignment, we're going to be drawing these and then filling in the coordinating network, which tells us how the current population and the water dynamics affect births and deaths. And then there'll be a second sector which will actually be the water supply. And this water supply is roughly modeled by this cycle here, where you have treated water, which can be used by the population in the city. But then after it's used, it moves into a stock of untreated water, where in order for it to be used again, it has to be treated. And so there's going to be a use rate, which is going to vary by the number of people in your city. And then there's going to be a treatment rate, which maybe only depends upon how much treated water is currently in there. And so these two things are going to need to be properly balanced to maintain growth in the population. And this is not necessarily a great model of the way water is treated in a city, but it's really just meant to kind of get us going in the process. So if you wanted to do a model like this for your final project, you probably would do something that would look structurally very different. And that's kind of on purpose here. Okay. So, and then the assignment, after allowing you to work with those two, will then have you develop a connection between these sectors. And that's the main part of the assignment. But then I'm also allowing you some bonus credit, where I'm saying, okay, now that you've built the model as I've described it, are there any other dynamical parts that you might want to add to it that you could bolt on to the side? So additional stocks or flows or variables to expand the boundaries of the model to include more dynamics that you might expect in a real model of a real city. And then another part of the bonus will be to go out to the web and just look for sources to find this, to set realistic parameter values. And so, for example, in this population portion, the average lifetime of a human living in this city is going to be a parameter that you're going to need here. Now, we're going to guess an average lifetime in the assignment, but you could go off and Google for, well, what are the average lifetimes of an American, living in an urban environment? And then so for this bonus, you could give me the sources and the parameters that you pulled from those sources to show me that you're able to go out and find data that, in a similar way, that for your final projects, you're going to have a bunch of parameters that you're going to kind of say, well, if I knew that value, I could model this thing. So as you're building the model, someone else in your group is probably going to go out to the internet, to the library, to whatever, and then try to find realistic parameters that you can then plug into the model. And so that's kind of what we're exercising here. Okay. So that's an overview of the basic structure of the assignment. What we're going to move forward on here is to get into kind of the nitty-gritty of where, because you're going to be asked to write some formulas in the assignment. So I want to review how to form those formulas in this presentation here. So before I go on to get into the finer details, are there general questions about the overall structure of the model that we're building in assignment E5? Okay. All right, so in that case, let's do a quick attendance question. And I will put the link in the chat. And so the question I have for you is, in assignment E5, what is the main task associated with the second bonus portion? So I mentioned that the first bonus portion is where you get to add on whatever other parts of the dynamical system that you think might make this model of a city and its water dynamics a little more realistic. And then in the second bonus problem, I said that you would do some other tasks. And so in that question, let's just roughly summarize what you're going to do for the bonus credit in the second part of this assignment, or the second bonus in this assignment. All right, and then before I get ahead of myself, make sure there's no web questions that have queued up. Looks like there haven't been. All right, so let's drill down into this modeling assignment a little bit more, so we have a better idea of where some of these formulas are coming from. So, one thing that you're going to have to do in this assignment is come up with the right formulas for things like the birth rate and the death rate for this population dynamics. And we have to think back to how we model populations when we were modeling like the bacteria example. And the hint that I have here is that birth rates act continuously over time. So we're not thinking about births that happen instantaneously. We're thinking about the average trend over a population. And you know that with the larger and larger a population, and the more asynchronous births get, then you can kind of assume that every, whatever, 8 seconds, you can imagine that there's a baby being born. And so you effectively can think about the human population growing as a smooth flow of kind of fluid humans, as opposed to discrete humans popping out every so many years. And so that's this averaging process is what allows us to kind of think of humans as a continuous stock. And so when we think about that, we have to think about formulating birth rates in terms of averages that we can then scale up to the level of the population. So if we think at the per person level, we can think, well, on average, the average per person birth rate, we can say, well, there's some people that don't have any children, and that's fine. There's some people that have a lot of children. So if we're just thinking about how many children on average does everyone, would we imagine, then you could do something like, you could say, well, how many people are born in the United States per year? And then you could divide that by, well, how many people in the population are even old enough that they could possibly have children, so, and then those things together might give you a number. And then that might say that, okay, so on average, every person in the United States has an average number of 2 children per year per person. I have no idea if this is the right number. This is just, just putting this in here. And so this would be, one, and this is kind of what I'm saying here, average number of children born per year divided by total population. And it might come out to be something like a 2 here. And then again, we're not saying that every person does have children, but we're saying that if we're modeling population growth, and we think about population growth at a population level, then for the purpose of our model, we smear out all of the production of children across the whole population to sort of imagine the average person in the population. Now, if I just chose the number 2, again, if I would have gone to the internet, I might have been able to actually figure out what the right number is here. But if I just choose 2 because I just want to get my model going, a question that I should ask myself is, does this number even make sense? Like, just back of the envelope, does it make sense that I'm saying every person has 2 children per year per person? Now, so this is in words what this number up here means. Every year, every individual on average produces 2 children. Now, the number 2 might seem realistic because maybe you thought that, well, on average, every person who has children has on average about 2 children per lifetime. But then you have to say to yourself, but that's not what I've written down here. I've written down 2 children per year per person. So that would mean that every individual in the population we're modeling, say the United States, is having 2 children per year, which for a single individual, that would mean that they're probably going to have to have twins and having twins every year. So this doesn't seem like it was a realistic choice of numbers. And so I have to then go back and think about what I actually meant in my mental model when I came up with the number 2. And the number 2 in my mental model was probably coming from me thinking 2 children every year for life is probably too frequent for humans. And so what I probably meant is 2 children over the lifetime. So, and then on top of that, not every individual is going to have offspring. And so I could imagine that even though on average, every offspring producing individual might have an average of 2 children, if I'm normalizing by the whole population, it might actually need to be even lower than 2 children per lifetime. So I have to think about, all of those things need to go in and out of my mental model as I'm trying to think of what the right formula for this should be. So now, let's go through the game of coming up with a formula that uses a little bit more mathematics, but comes up with something that's probably a little bit more realistic. So that's what we're about to do, is to build that formula. Before I go on, are there questions about that? Is it clear that, that I need this number, which is average per person birth rate, but 2 per year per person seems like it would be way too high of a number. And so I need a formula which tells me how to take the intuition from my head and turn it into a number which doesn't make, which isn't nonsensical when I actually put it down on paper. Does this make sense so far, that we need to do a little bit more work in order to figure out the average per person birth rate? Okay. All right, so how do we come up with a more realistic formula? Again, trying to use our mental model combined with a little bit of mathematics. All right, so let's think about some assumptions that we're going to make on the, on breeding in a human population that we're modeling in this assignment. And so one assumption we have to make is maybe that humans have to form pairs to produce offspring. So, so this is different than even the fish example. We didn't really talk about formally modeling how fish have to form pairs. In the bacteria example, we assume they don't have to form pairs to produce offspring, but in humans they do, because humans only reproduce sexually. And so even though you have 350 million people in a population, then even when you've accounted for how many of those aren't of reproductive age, then you can't assume that every single one of those individuals can have offspring in isolation. Now, so we know they have to form pairs. And so then we are going to look to the internet, and maybe on the internet, we'll find out that every pair in a human population produces about 2 offspring over their lifetime. So again, you have to look to the internet to figure out what that number should actually be. This is complicated by the fact that, people divorce, or people don't marry, and they might have multiple partners. And, so a tidy little world where every single individual pairs up, marries for life, and produces 2 offspring is much easier to model, but that's not the world we live in. And so we have to kind of find this balance between the real world, which is really complicated in how human reproduction works, and an approximation that is going to give us dynamics which, when you zoom out and look at the population level, tend to match. So the microscale dynamics are not necessarily going to be exactly what goes on, but the macro scale dynamics end up working very similarly. So that's kind of what we're shooting for here. That's why we're really focusing on average behavior. So the average pair, I should say, we're going to say produces 2 offspring over their lifetime. So then we have to figure out what the heck a lifetime is. Well, we're going to say that each pair pairs up once and sticks around with each other for 70 years. So we're saying that every lifetime is about 70 years. Now, I've mentioned there's a bunch of problems with these assumptions. That there's, this first one about how humans pair up, well, that may not match with exactly all of the different ways that humans relate to each other sexually. There might be demographic differences in offspring production. It might be that those who are more affluent have a different number of offspring than those who have a harder time finding resources. You find that across a bunch of different primates, there's these really interesting patterns where the sex of the individual that is that ends up moving from tribe to tribe often ends up so there often ends up being these interesting correlations between, so it has to do with like upward mobility. And so there's these interesting patterns where if you, in different primate groups, and so in gorillas, bonobos, humans, whatever, then you end up having these consistent patterns that you end up seeing that you get an overproduction, like more offspring produced in groups that tend to have access to fewer resources. And those groups tend to export more offspring out and into groups that they can incorporate into more kind of affluent groups. So there's these weird, interesting social dynamics, which seem to have been produced over, selective pressure over millions of years to allow for kind of an upward mobility, to allow for resource availability to become more available for offspring. So you end up finding that individuals at the top of this kind of resource ladder produce fewer offspring and hold on to their offspring more, where those at the bottom actually produce more offspring, even though those more offspring do poorer, because there's a greater chance that some of those offspring in future generations will be able to find their way in higher. So there's all these weird dynamics that we are totally, that's just across species. Even within species, there's even these weird demographics in offspring, demographic difference in offspring production. Of course, changes in lifetime, those can vary depending on where, if there are any conditions that certain individuals are predisposed for, et cetera, et cetera. This could affect, lifetime. And then there's, the multiple matings, that is something which is not being modeled here. There's questions here about, couldn't you also talk about cultural problems, political bans? So it's exactly right. There's tons of different things which we are not modeling here, but absolutely, definitely change how reproductive dynamics work. If you look at reproductive dynamics in China versus the United States, if you look at reproductive dynamics in the UK versus Italy, I mean, across all of those sorts of things, there are definitely things that really matter. But we are just kind of trying to make a first order approximation with the assumptions are up here. So again, all models are wrong, but some are useful. And so the basic idea here is we need to come up with some basic assumptions. Even though we understand that they're flawed, they are a lot better than just the number that I pulled out of nowhere. And so that's really what our assumptions do. Our assumptions can be attacked because they haven't modeled, because we haven't made enough assumptions. But we've actually ended up trying to make just enough assumptions to give us a little bit of tractability without making so many that we end up making this completely specialized to China or completely specialized to the US or so on. So I recognize that the model that I'm about to produce here isn't perfect, but it's a lot better than just picking two out of the air. All right, so if we take all of these assumptions here, recognizing that there are problems, we can start building up a formula. And that formula is saying, well, if we want the average per person birth rate, then what we're going to do is we're going to take all of these things that we've collected here and put them into kind of a mathematical combination. 2 children per lifetime per pair. That's this, this is this kind of these first two here. 1 pair per 2 people. So that is what allows us to go from our population numbers, which are in terms of people, and our reproduction numbers, which is in terms of pairs, and 1 lifetime per 70 years. So if I combine all of these things, then hopefully I can get these back down into units that I want. And those units that I want are going to be children per person per year. But in order to get to children per person per year, I had to create these 3 things here, which in the next slide, I'm going to do a lot of cancellations so that my units end up being children per person per year. But I want to make sure that you understand where this formula comes from, because these are the types of formulas which you're going to start playing with on the assignment. So there are questions about where this formula comes from, where I'm just saying 2 children over an entire lifetime of a pair. And every pair represents 2 people, and every lifetime represents 70 years. And so it's like these 2 parts here are a way to translate the terms that are in this first line here, so that after I do the translation, this whole thing is going to turn into children per person per year. So are there questions about this formula before I cancel a bunch of things to turn it into something much more compact? Okay, as we sit here and stare at that, I am going to check the web here for any other questions. All right. Okay, so what I'm going to do next, I'm going to hit next on these slides, and what we're going to see is a bunch of these extra units popping off as they get canceled off here. So if I just turn on my pen here, then I'm going to see that lifetime here is going to cancel with lifetime down here. so that I'll end up getting a 70 in a denominator. And this pair here is going to cancel with pair here, so that I end up getting a person or people in the denominator. And so let's see what ends up happening with that. So if I go to the next slide here, then what I see here is this is my 2 children per pair. This here is my 1 pair per 2 people. So that turned into a 0.5, 1 divided by 2. So those things are going to end up canceling each other out. And then this is my 1 lifetime per 70 years. So that is a conversion into the 70 years. So now this whole thing, like we end up saying these things will end up canceling out, this becomes, instead of having 2 children per person per year, which is way too fast of a growth rate, now I have 1 divided by 70 children per person per year. And that is a much, much smaller number. And so those things can be combined together into this average per person birth rate. And if I need to create a births flow, which goes into my population stock, then that births flow is going to be this average per person birth rate constant, which has come from me formulating it based on these assumptions up here. And then each one of these, so this is children per person per year. If I multiply it by population, then that is going to end up getting rid of the per person here, so that births will be in children per year. And so that's what I end up getting here. Births is the flow going into the population. So if I've got my stock down here, I imagine this is a population stock, and it's got births going into it and deaths coming out of it. And I formed my my flow here. So this is the little flow valve, and this is the little flow valve for deaths. And this makes it clear here that I'm going to have a link from population back to births, just like we did in the bacteria case. And that population is going to get scaled by this constant. So you can imagine I might have this constant sitting out here, and it is going to also go into this flow variable, so that inside this flow expression, it's just going to be that constant times the population, and that will be the flow rate causing the population to grow. All right, so are there questions about that formulation? Does that make sense, how I got a formula for births? And not only does it make sense how I got the formula for births, but I'm hoping you can see from these assumptions here how you connect real world data into these formulas. As you make a couple of assumptions to how to break the formulas up, so that once they're broken up into chunks, those chunks start looking like recognizable statistics that you can go out and find, out on the internet or in the library, or asking, expert sources. And so you can go to someone who studies these things, a social scientist, sociologist, or whatever, and or someone who studies public health, and you can ask them, what is the average lifespan, and that's where this 70 years comes from. What is the average number of children that a American couple has over their lifetime? And they can, you can look that data up, and you can say, well, you have about 2 offspring, those sorts of things. So these are stats that you could potentially look up and then combine together into these formulas. So are there questions about how we put that together? Does that seem pretty clear? All right. Well, I'm going to skip that attendance exercise. So there will be other formulas that you're going to have to set up inside the assignment, and you'll work through those as we get to them. But so now I'm going to move on to a different reminder, which if you haven't played with this for a while, don't forget about our time units and our time step, DT. So just as a reminder, inside Vensim, you go under Model and then Settings, and then that reveals this model settings here, where you can set your DT value, which is your time step here, and you can set your base units, which if you don't specify any time units anywhere or any conversions, this is what is going to be assumed to be the time unit that you're working in. And the DT value that you set, you can start with a value which is, say, 1/100th of the fastest thing that happens in your model. So if you have a time scale of something that is going to produce, say, 1 offspring per day on average, then you probably need to be simulating at 1/100th of a day is your DT. If you produce 1 offspring per year, and that's the fastest thing that happens in your model, then maybe simulating at a day resolution is probably going to be fine enough. So that, but ultimately, you should probably run a couple of different DTs and make sure you've chosen a DT small enough that if you choose a DT smaller than that, your results don't differ that much. So that's where you find DT in Vensim. Remember that in Insight Maker, in your Insight Maker, there is a settings up at the top of every Insight Maker model. And then it has a very similar setup as in Vensim, where you can choose your time units here, and then you can choose your simulation time step. And that, again, is where DT is located. So same rules there about choosing a DT. Maybe start out with 1/100th of the fastest thing that occurs across your model, and then run a couple of simulations with DTs that are slightly smaller and confirm that at smaller DTs, you get still the same results. So any questions about that? Setting DT in your time units. And by the way, if it looks like I'm fidgeting, it's because the dog has found his way in and is chewing on my hands. So if you notice that, that is what's going on. Okay. All right, so more recent stuff. You will use lookup tables in this assignment. So you've got some practice on using lookup tables in question 1. I have received at least a couple of questions about question 1 of assignment E2 saying that, this diagram or this that I'm getting out, I really think I drew it correctly, but the behavior over time that I'm getting doesn't look like anything that I'm familiar with. Where have I gone wrong? And so far, my response to that has been, well, why do you think this looks like the wrong behavior? Because in most cases where I've gotten this email from students, the behavior that they're seeing is exactly the right behavior, but it's just starting from initial conditions that maybe are not as familiar. So I put a hint in a recent announcement and on Slack that reminder that for assignment E2, for question 1 of assignment E2, remember that you're starting when we're assuming that the fish in the fishery have already reached carrying capacity, and we are adding boats at that instant. We are not starting, as we've done in the past, when the fishery is empty of fish and we're adding fish into it. If I would have started that, if you add boats to a fishery at the same time you add fish to a fishery, then the fish aren't going to get a chance to grow to a big enough population to be able to achieve sustainability. And the boats, basically, you're going to put a fish in and the boats are going to find it, pull it out, and you're immediately going to go extinct. So that's the reason why we have to let the fish population reach its carrying capacity before we introduce the harvesters. And so, but the other side of that is the diagrams that you'll get for your plots are going to look a little different than you expect, but that's not necessarily a bad thing. So as you start simulating question 1 for the assignment due this weekend, just keep that in mind, that the plots might not look like what you're expecting, but think about them and see if they make sense based on how you've set the initial conditions up. All right, so you will use a lookup table in that question 1, and you're going to use a lookup table in this assignment as well. And so as a reminder for lookup tables, you go into Vensim, and when you go into the equations, you'll end up hitting this auxiliary under type here. Leave that as auxiliary. There is a lookup table that you can find here, but it's kind of a more advanced way to use a lookup table. And if you'd like to play with it, that's fine. But if you're looking for the more conventional way to use a lookup table like it's used in your book, leave that as auxiliary under type. And then under subtype, say with lookup. So when you're asked to build a lookup table in the assignment, you're going to, there's a lot of students I know that are going to end up just, their gut is going to pull them towards that type and change this type to lookup. But remember, that type should be auxiliary unless you want to get advanced. But then the subtype should be what says with lookup. So that's something important to remember. Then the input that you've drawn connected to the lookup table, that input is going to show up down here. And you're then going to put it in here under with lookup as the thing this is like the x-axis of the lookup table, like the independent variable of the lookup table. So you just put that in there, just you just pick it here and you put it in there. And then the last thing left of that is to go up here to do the as graph. And that is what's going to help you populate what goes down here in the actual lookup table. So if you go into clicking on that as graph, that will bring you to the this screen that allows you to enter in a lookup table. You can either enter in every point in the lookup table manually, like over here, where like this 0, 0 is this point here. So that's this one, this 0, 0 is that point. And for example, this 0.6550, that is this point up here. And so every one of these little dots here represents a point in this table. So you can either manually enter in all of these points, or you can use your mouse and click on these points. Now, something that you should be careful to do is, especially if you're using the graphical method to click these in here, is adjust the vertical maximum and vertical minimum so that they cover the full vertical span of the points that you want to put in. Even more important, adjust the horizontal minimum and horizontal maximum so that you cover the whole range of values that can come in as your input value. In this case, fish density, we know, goes from 0 to 1. So I need to make sure that my lookup table also goes from 0 to 1, or else if I get a fish density, like if I built my lookup table from 0 to 0.8, so it ended here instead of out here at 1. If the simulation ran and it generated a density of 0.9, then I'm going to get an error. Vensim is going to complain because 0.9 isn't something I specified in my lookup table. And so in order to prevent those errors, I need to make sure that my lookup table covers all possible values that could come in as whatever I've specified as the input of the lookup table, which in this case is fish density going from 0 to 1. So once I've drawn that lookup table, and this is like the lookup table you'll draw in your homework due Sunday, then that will end up generating this lookup table line. If you really are advanced, you can manually type this thing in. If you kind of learn that these are like the corners of the graph from the bottom left corner to the top right, and these are all of the points of the lookup table, and then you don't have to use the as graph, but it's totally reasonable to use that as graph to specify that. And then that's how you do the lookup tables in Vensim. It's a similar story in Insight Maker, and I'm going to remind us of that story in the next slide, but I want to pause there. Are there any questions about this lookup table, or about lookup tables in general, or about entering them in Vensim? And this could help you on this weekend's homework, and this could also help you on this homework that'll be due next weekend. Okay. All right, so let's see how to do that in Insight Maker. So in Insight Maker, they have a special primitive. So you click on Add Primitive, and it's called a converter. It shows up. It has this different shape and different color. So you can pull on one of those converters, and then in the nav bar that's on the right-hand side here, you can pull that thing out. And what you can change its name of the converter, for example, and then you can configure this converter here. And so by default, I think it uses interpolation linear. That makes it, the lookup table operates exactly as it does in Vensim. Also, by default, it uses an input of time. And that input of time can be useful if you want a pattern to change over time, but very often you want the lookup table to depend upon an input coming into it. So you are going to draw, from some other variable, an input coming up here into the lookup table, and then on your input source, you'll change it from time to whatever this variable is that you've connected to it. So from there, you can click on the little equal sign that shows up when you mouse over your lookup table. There's a little equal sign that'll pop up here, and that'll pop up this thing, which is like the as graph in Vensim. And so from there, you can enter in all of the points of your lookup table down here, or you can click them this way, as by clicking on the graph itself. So you can either click add point to add points, or do that, or you can actually create a list of points in Excel on your computer, or if you had a list of data from you had data that you're trying to mimic from real world data, you can import that real world data into your lookup table right here in Vensim. This interpolation linear that I was talking about is what causes these points to have this oblique, this diagonal looking. So every point is connected directly to the next point, just like it is in Vensim. If you instead change that to none instead of linear, then every point that you put into here just holds its value until the next point and then jumps directly to that next point. So that's just two different ways to draw the same to draw a lookup table. Sometimes you might want to do the hold, where basically that means any value that comes up in between two values that you've specified is going to go to this value here, which is just the held value of the previous point. Or if you would have done linear, which would connect a line in here, if you had a value in between, it would go to an intermediate value in the lookup table instead of the previous value from the previous point. Okay, so any questions about lookup tables in general or lookup tables in Insight Maker? And again, the role of lookup tables is to allow you to make a relationship between a variable and another without having to figure out a mathematical way to characterize that relationship. That you could just graphically say that as one variable changes, I want the other variable to change in this particular way. And that relationship, which you could just draw out graphically, can be captured in a lookup table, even though you don't know a particular mathematical formula that captures that relationship. Okay. All right, the other thing I wanted to remind you of are these shadow variables. And so in Vensim and Insight Maker, in Vensim, they're called shadow variables. In Insight Maker, they're called ghost primitives. So in Vensim, if you go up here and hit on shadow variable, you can then create a shadow variable like this one, and it will end up having a gray color, and it'll have these little angle brackets around it. And when you create it, it says, well, what do you want to be your shadow variable? It'll pop up this dialog box, and it will show you every variable that you've created, stocks, flows, anything, will be in the list, as well as a number of other variables that are always behind the scenes that you can get access to this way, like the time in the simulation. So the clock, in whatever time units you specified in your model settings, that counts that much time since when the simulation has began. And then that number off that clock comes out of this time variable here. And that shadow variable allows you to create aliases to existing variables that can clean up things if you want to make long range connections. So you've drawn a very complicated, sector 1 you've drawn here, sector 2 you've drawn down here. And rather than drawing a bunch of connections across these two sectors, you can create shadow variables that are down next to your other sector. And those shadow variables are just going to be copies of what's in the other sector. But then from those shadow variables, which are closer to the sector you'd like them to connect to, then you can draw connections. And then that way you don't get this web across your sectors, which sort of makes it harder to see that you've got two sectors separated out. So that's one way you commonly use shadow variables and ghost primitives, but they also can be used to access things like time, which are useful in Vensim if you want to use time with a lookup table to create a pattern, say a seasonal pattern. In Insight Maker, same story, but if you go to this add primitive, way down at the bottom here, there's a ghost primitive that is exactly the same as a shadow variable in Vensim. It creates a kind of ghostly copy. So you can sort of click on a variable that you like to make a ghost primitive, go down to ghost primitive, and it will create a linked, like it says here, linked alias of whatever primitive you used here. And then you can take this ghost variable here, drag it around and put it wherever you want. And whatever happens to the original will also happen to that one. So it just, again, allows you to create connections without long wires across your diagram. So that's all I'm saying here. All right, any questions about that? The ghost primitives, shadow variables? Okay. So in that case, as you're thinking of questions, let's do one more attendance question. Give you guys credit for listening to me drone on here. And that question is, what are shadow variables called in Insight Maker? So they're called shadow variables in Vensim. What are they called in Insight Maker? Okay. All right, so then another thing I want to cover here, which is sort of connecting and extending on all the things we just talked about here. And this is particularly useful for some of your final projects if you want to simulate seasonal patterns. So a lot of times I have people, so I've had students in the past who build simulations of power usage that involve simulations of power usage across a year in Phoenix. Now we know that power usage varies seasonally. People turn on their air conditioners a lot more in the summer than they do in the winter. And so, so sometimes you need these kind of background seasonal variations where you get these huge increases in demand in the summer that fall off in the rest of the year. So how do we generate these periodic patterns inside Vensim or Insight Maker? And so one way to do that is to make use of these lookup tables. And so let me show you how to do that. So the idea here is that what I would like to do is create a time variable like this one that doesn't give me a raw number that tells me how long it's been since I've ran the simulation. It gives me a repeating number, which tells me something more like what month is it? Or, so that way it'll climb up to 12, but then once I get into the next year, rather than going to 13, 14, 15, which would be the number of months since I started the simulation, it will then reset back down to 0 or down to 1, depending on how we're counting. So that's what we like to have here, is a kind of cyclic time where it's not keeping track of how long since the beginning of the simulation, it's keeping track of how long since the beginning of the current cycle that I'm simulating. And if I had this type of cyclic time, then I could combine it with a lookup table, which only represents, say, a year's worth of the pattern. So this way, if I simulate 10 years, if I used raw time, not cyclic time, my lookup table would have to actually simulate all 10 of those 10 years. Which is kind of a pain, especially if I want to then go from 10 years to 20 years, then I need to update my lookup table to go across all 20 of those years. So what I'm trying to do here is if I create something that is just going to keep track of where I am in a year and keeps resetting as I go to the next year, then my lookup table only has to represent a single year pattern. And this combination of the two of them will end up giving me my 10-year oscillations, where I'll get the 1-year oscillation, the 2nd-year oscillation, the 3rd year, and so on and so forth. So the real question is, how do I generate this cyclic time? And there is a particular operator inside Vensim and Insight Maker that allows us to do that. And it is called a modulo operator, or the modulus operator. And so you can go into Insight Maker, And I can, when I create this variable, I hit the little equal sign up here that shows up when my mouse goes over it. And that is going to pop up the equation for this variable. And then I can, in the little nav bar on the right-hand side here, the hints, there is a time functions. And this time functions is cool because it allows me to do a unit change very quickly on the time to a wide range of other units. And so even though my base time units might be in seconds, then I can use the months here, months, that will automatically tell me what number of months it's been since the beginning of my simulation. Now I can combine that with this thing called a mod or modulo, and and then I put a 12 after that. Now, what does this modulo do? And I'm just making sure that I don't have. Yeah, I'm going to step through this here. So time functions. That's where I can get all these different times. I can pick out months, which is what I was doing here. And then I can focus here on this thing called the mod operator, modulo. This gives you the remainder when dividing by whatever number that comes after it. So when I have mod 12, what that's going to do is take whatever number is here, and it's going to divide it by 12, and then look to see what the remainder is, and that is what's going to pop out here. So this mod 12 here that effectively turns the months into a number that's between 0 and 12, but is strictly less than 12. It's the remainder when dividing by 12. So, and I'll show a more concrete example of that here in just a second. And so the idea here is that 12 is the number of time units in the cycle before the cycle repeats. And so the idea here is if months goes from 0 to infinity, so in the very first month, it's going to come up 0. In the second month, it's going to say, we've gone through 1 month, and so it's 1 and a fraction month. So months will read 1, and then 2, and then 3. And this can go up, like I said, to infinity. By adding the little mod 12 on it, then what that does is ensures that the first 11 are match exactly. But the instant the time goes to 12 or higher, it maps the 12 down to a 0, because if you divide 12 by 12, you have a remainder of 0. If you divide 13 by 12, you'll have a remainder of 1. If you divide 14 by 12, you'll have a remainder of 2, and so on. And so this is going to turn months, which just counts up to infinity, into something which counts up to 11, and then this works for fractions as well. So it'll go 11, 11.1, 11.2, all the way up to 11.99999, and the instant it hits 12 months, a full year since the beginning of the simulation, then months mod 12 resets and goes back down to 0 and starts over again. And then that will start over again at the 3rd year, and then again at the 4th year, and so on and so forth. And that's all I'm kind of showing here. And then, like I said, this also works with fractions. So months is going to give us fractions of months. So if you've only run for half a month, it'll come up 0.5. And so likewise, once you hit 12, it'll get mapped to 0. 12.5 will get mapped to 0.5, and so on. All right, is it clear what this mod does? And I'll show you how we implement that, or how we use that in the lookup table in the next slide. But right now, I want to make sure everybody feels good about this mod being just divide by the thing that's here in the circle, and then take the remainder. This is just a remainder operator here. Any questions? Okay, good, great. This is kind of abstract. A lot of students at this point have maybe never encountered the mod before, but just think of it as remainder. We usually focus on quotient. In this case, we're focusing on remainder. Now, what can we do with that? Well, what's cool about that is that I now can take that 0 to 12 the output that will never, ever, ever be higher than 12. And I can use that in a lookup table. And in that lookup table, the input for that lookup table, I now know is going to be between 0 and 12. I don't have to worry about that. I'm simulating 100 years. I don't need to put 100 years of pattern in the input to this lookup table. I can choose a generic year and put the pattern that goes on for that generic year, and this will automatically repeat this pattern over and over again. And so this is like what happens at the beginning of a year. This is what happens 1 month into a year. So this output, this could be, for example, energy use. And so starting from the beginning of the summer in Phoenix, for example. And so maybe at the beginning of the summer, energy use is at baseline levels. But once you get into the middle of the summer, maybe this is spring. So in the spring, energy is at baseline levels. But by the time you hit the summer, then energy is at the highest levels. Then in the fall, that comes back down, and in the winter, and then finally in the next spring, you're back down to the same baseline levels. And then that repeats year after year after year. But I only have to specify what it looks like for a generic year, and then Insight Maker or Vensim will automatically repeat this thing over and over again because of that cool modulo operator, which is constantly resetting time. So to show you that, so if I were to take this, this lookup table here, so again, this is just stepping through this. The lookup table is only defined from 0 to 12, and that corresponds well because the modulo operator is only going to produce numbers between 0 and 12. And if I were then to simulate this whole thing, then I can see that I've simulated 24 months. And then what have I plotted here? Well, this green thing, this is my cyclic time. And you can see cyclic time from 0 to 12, it just climbs up straight line. But when I hit 12, it goes back down to 0, and then it climbs again. If I take that climbing cyclic time, as I'm calling it, and I run it into my lookup table, it produces that lookup table's pattern, and then it produces that lookup table pattern again. So I could simulate 2 years by only modeling what happens on 1 year. I could change my end time to go to 48 months or 96 months or 100 months, and it would just keep repeating this seasonal pattern over and over again. And so that is all that I think I'm pointing out here on these slides. So is it clear? Are there any questions about that in the Insight Maker case? And then I'm going to show you how to do the exact same thing in Vensim in the next slides.
I have a question.
Yes.
Would you include the cyclic time and the other repeating pattern if you were like answering a question or a certain question, like for graphical analysis?
Well, so normally I wouldn't plot this cyclic time down here. I'm just doing that for you to kind of demonstrate. Does that make sense?
Yeah, it does. Thank you.
Mm-hmm. Yeah, this is kind of an interesting example where in the model, we have introduced something that is not actually important. This is just an artifact that we use to program the model to do what we want it to do. But we would never show this to a stakeholder, because then a stakeholder would say, what the heck's cyclic time? And in reality, we might bundle this whole thing up into a sector, which just is like seasonal pattern or something like that. But when, in the nitty-gritty details of it all, then we, as programmers, needed to build a cyclic time to allow to, as our way of translating to Insight Maker what we want it to do. Whereas in the real world, we take for granted that we can have seasonal patterns that automatically repeat. All right, so how do we do that in, any other questions about that? So how do we do that in Vensim? So far, everybody's sort of been giving me the feedback that they like Vensim more than, they don't necessarily like Vensim, but if you put a gun to their head and you said Vensim or Insight Maker, I think most people are leaning towards Vensim right now. And so in that case, how do we do this in Vensim? So in your model settings, again, this is where you set your DT. You should make sure to set your units for time small enough to capture your repeating phenomenon. So if you want things to repeat over a year, then you want to make sure to set these to like months so that you can specify what happens at a month by month time scale. So, so that's kind of what I mean by make sure your units of time are small enough so that in a lookup table, using those units, it's easy to specify what this parameter is. So in this case, I could set it to seconds or months or whatever. Now I'm going to use a shadow variable, time, and I am going to create a, this is like my cyclic time here. I'm going to create a repeating pattern variable that time is going to go into, and it's basically just going to create that cyclic time. I don't recall why when I originally made this slides, I didn't call this cyclic time. I think it's because I end up bundling the lookup table with it together. So what we're about to see in the next slide, if I recall correctly, is that I am effectively doing both the cyclic time and the lookup table in the same variable together rather than creating two separate variables. So there's the shadow variable that's sitting out on the side, and then this one thing is going to do everything together. So this repeating pattern, let's go in and drill down into it, see what it looks like. Then I'm setting this up auxiliary with lookup as a lookup table. But the input that I'm going to use for my lookup table is not going to be the raw time. It is going to be time after it's processed by this modulo operator. Now, the mod operator in Vensim looks a little different than Insight Maker. Instead of being time mod 12, like it is in Insight Maker, then it is modulo, and then you do parentheses time, comma 12. And you can find it if you go down here in Insight or in Vensim, there's a little functions box. And I think usually this is set to like popular or something. If you click down there, you can change it to all, and then you can scroll through all possible functions that you can use in Vensim, and you'll find the modulo there, or you can just type it in manually, modulo. But if you click it here, then it'll fill in the arguments with little reminders of what argument each argument does. And so I then put my raw time in here, and then I put the repeating period in here. Because I have set my time up to be in units of months, then I use 12 here, because I know time is going to, its repeating pattern is going to repeat whenever, I wouldn't want it to repeat whenever time hits 12. So I want to make sure time is in units of months. So I set time to months, and then I know it's going to repeat, it's going to produce a year whenever this time variable is equal to 12. And then that's why I'm making this modulo time 12. And it produces the same thing in Insight Maker as doing time mod 12. So that's all that I'm saying here. Configure the lookup table that uses modulo time 12 instead of time, the same way we did in Insight Maker. So I'm going to click on as graph. And then that's going to take me, just like an Insight Maker, to something that looks like this. I'm going to configure my x-axis to start at 0 and end at the length of the repeating pattern. So I want the pattern to go up to 12 and then reset. And so 12 is the highest number that modulo is going to produce. And so I make sure that this goes up to 12 to at least that number. And then I can set my Y max to be whatever allows me to see this pattern effectively. I can either enter these in manually, or I can click them in with my mouse in my lookup table here. And this is going to say basically at the beginning of the year, this is what the output's going to look like. Somewhere in the middle of the year, this is what they're going to look like. Towards the end of the year, this is what they're going to look like. And then they're going to repeat. So at the beginning of the next year, they'll be back down here again. So if I do all of that, I put that together, and if I simulate and just plot my repeating pattern, then I get that same thing I drew in my lookup table here. And then I get it repeating again because my time extends past a single year. And so if I did a third year, I would get the same pattern again, and so on and so forth. And that's how I create cycles in Vensim. All right, so are there questions about that? That's the last kind of topic that I'm covering here today. Okay. All right, so announcements then. So this is just reminding us of the stuff I started talking about at the beginning. Chapter 8 is going to be due, I think, a week from today. If you look online, I've actually specified you don't have to read the entire bit of chapter 8. You can read up through page 293. And I believe I have perusal configured, so it only shows you pages up through 293. And that way you get full credit. Well, so, if you haven't figured out, perusal, it gives you points for a bunch of different things you do. And one of the things it gives you points for doing is actually reading through the whole chapter. And so it will then, that way, it's stopping at 293 ensures that it gives you full credit for reading the portion of the chapter I said to care about. If you'd like to read more of the chapter, I certainly welcome you to do so. And you can go back to the main Canvas page where I've included the PDF for the chapter, and you can keep reading there. But the perusal one is only requiring you to go up through 293, and that's all I'm going to sort of test you over in the assessment and the exercise. And then the last 2 chapters of the book, we are going to be reading those for lectures F2 and F3. And so if you do get done with chapter 8, I encourage you to keep moving on chapter 9 and 10. And what we're going to see in chapters 8 and 9 is that they're just case studies where we're applying system dynamics modeling to different types of systems. So you can get an idea of the different things you can do with system dynamics modeling and the different ways you can build these models. So they're meant to be examples. And then in chapter 10, we go back to sort of thinking about the modeling kind of more broadly, again, kind of, circling back to where we started at the beginning of the class. And that's, and then the only other content that we have of the class is another lecture that I give introducing you to chaos theory and randomness and the differences between the two of them and how you implement chaos in a model like this. And then there'll be another lecture that Eric will give that will introduce you to some of the quantitative work that he does when he actually goes out and does research. And so it'll give you kind of an idea of if you were to hang around for grad school and to start, using quantitative frameworks and sustainability applications, what might that kind of look like? And I promise that there will be at least one question on the final exam, which will be taken from the material that Eric will present in, I think, the last formal lecture of the class, if I remember correctly. Okay, and then so short term, you've got assignment E2, don't forget about that. That is due on Sunday. And then assignment E5 is now formally released to you, but it's been available there. So we will work on that together in Tuesday's class. So there's no formal lecture for Tuesday's class. It's just we're going to break up together or break up in maybe groups, and then we'll float around the groups and then help you get moving on assignment E5. Many of you might finish the whole assignment while you're in class, but those of you who don't, at least you'll get a lot of momentum build up on it. So again, due Sunday, there's a muddiest point, there's assignment E2, and then this is kind of our timeline moving forward. So I will finish up today with the last attendance exercise, and then I'm happy to take any questions you might have. Otherwise, I'm happy to wish you a good weekend. So attendance question here is going to be, what is the solution to 15, or I'll do it in Vensim language, to modulo 1512, which in Insight Maker would be 15 mod 12. And again, that's all I've got for you today. So if you have any questions, please feel free to ask. Otherwise, have a good weekend.
Are you asking in the attendance question, like, for instance, like, do you mean every 12 months? Like, are you asking like for like us to like say every 12, like every, yeah, just give you the number?
Mm-hmm.
Okay, thanks.
Yep. And if you need a hint, 17 mod 12 is equal to 5, or modulo 17, 12. And I guess maybe I'll throw in another hint just for kicks. 25 mod 12 is equal to 1. And then, like I said, that's all I've got for you. So if there's no other questions, then I'm happy to end the meeting. I think I do have office hours today if I got my days right here. So I'm also happy to meet anybody for office hours if there's any other questions. Don't forget the project proposals, the revisions are due this weekend. If you want to make revisions, if you don't, you want to keep your old grade, that's fine too.
Actually, can you explain the attendance question to me again? Is that possible?
Yeah, so all the attendance, so yeah, so the attendance question, maybe I'll just stop the recording for and then I can just be a little more specific.
Thanks.